Okay, we'll start with number 1. Number 1 is x squared plus y squared equals 36. Okay, we're talking about implicit differentiation, and the counterpart to implicit would be explicit. The difference between an implicit function and an explicit function is that it's the same between an explicit rule and an implicit rule, like in society. Something that's implicit is unspoken, it's unuttered. Nobody tells you it, you just know it. Like, it's implied that you don't drive your car through someone's living room. It's uncouth. You don't do that. Nobody tells you that. As you're, in driver's ed, it never comes up. They never tell you that. But it's implied. Of course you wouldn't drive your car through someone's living room. And it's the same way here. Y is not explicitly stated as y is all this, is equal to, y equals all this other stuff with x in it. It's implied that there's a relationship between x and y. It's just not explicitly stated. And when I say explicitly stated, I mean y equals stuff, right? So it's implicit. It's implied that there's some relationship. And so implicit differentiation would be the way to differentiate something that's implicitly stated. Now, for this one, actually, if you look at it, we could do something like this. And y equals the square root of negative x squared plus 36. Oh, now it is explicit. Y is this stuff. And then we could differentiate. We could say dy dx is equal to, we're going to take the derivative of this. Okay, so this is a function of x. It's inside another function, the square root. So we need to use the chain rule. So if we think of this as to the 1/2 power, as we did last time in our chain rule video, so it's to the 1/2, so I bring down that 1/2 power. I don't change anything about this function inside here. I leave it alone. And then I would, of course, subtract 1 from the power, giving me negative 1/2. Then I would multiply it by the derivative of the inside function, negative 2x. And there we go. We've taken the derivative. And so, you've outsmarted Newton, and you didn't have to use implicit differentiation. But what about a problem like this? Number 7. X to the third, y to the third, minus y equals x. Now I dare you to even try to express this explicitly. Seems possible, but messy, really messy. So we don't want to mess with it. What we want to do now is use implicit differentiation. And let's just go ahead and start doing that. And let's break it down a little bit. Since these y's are in here, it could be a little confusing. But look, we have this function that we need to take the derivative of. And because of the sum and difference rule, I know that this is a difference of two functions, and so I can take that separately, and then this is its own function over here, and I'll take the derivative of that. Okay, so let's start with the purple. We look at what's in the purple, and we see a function times a function. So I know that I'm going to need to use the product rule. That's how I take the derivative of a product of functions. So we started on the product rule, derivative of the first times the second, plus the first times the derivative of the second. So now this is the issue here. How do I take the derivative of this? You might just think, hey, 3y squared. And you're kind of right, but not all the way, because when we take the derivative, we take it with respect to some variable. Okay? And to remind you of what that means exactly, remember that the derivative at some point is the slope of the tangent line. And the slope of a line is the change in y over the change in x. That's what these deltas mean, is change. Right? And we represent remember that the derivative, that slope, is the limit as we let 2 points get really, really close to each other so that the distance between them is just incredibly, unimaginably small. It just becomes negligible. So we represent that by dy dx, d being this incredibly small change. And you'll notice that it's the change in y over the change in x. X is the run, rise over run. X is the one that is changing, in the horizontal direction. It's the independent variable, and it's the one that is the change in the denominator. So that's what we say. We take the derivative with respect to x. As x changes, how does y change? So when we take the derivative with respect to a variable, the only functions that can be differentiated simply, just with the basic rules that we learned, say in the first section that we covered them, the power rule and the sum and difference rules and all that kind of stuff, is something with purely x in it. But once we have something else in there, something more than just x, we have to apply the chain rule. And remember, I said it's implied that y is some function of x, that it has some relationship directly with x, that if I knew x I could find y. It just would take a lot of work to express it explicitly. But we just treat this as the inside function. Y is the inside function here. So how do we take the derivative of this if this were some other function of x, which it is? We would use the chain rule. And so we take the derivative of the outside, which is actually what we've already done, and then we need to multiply by the derivative of the inside function, What's the derivative of y with respect to x? Well, it's just dy dx, the derivative of y with respect to x. So we would multiply by dy dx. Okay, we've been doing this all along. Y equals x squared. Take the derivative of both sides. Dy dx. We didn't even think about it. But we took the derivative of this side with respect to x. That's exactly what it is. The derivative of something has to do directly with the slope, and that's the slope. That's the slope of that function at some point with respect to x. So now we move on. We've done the product rule. We use the chain rule here. And now we're going to work on this one. Well, the derivative of this function is just dy dx. And then on the other side, the derivative of x with respect to x is 1. So now what we need to do is, what we wanted was the derivative of y with respect to x. We always want dy dx, or y prime, or what have you, however you call it. So we need to solve for dy dx, isolate it. So that's exactly what we're about to do. Let's isolate it. So here we've got x squared times 3y squared times dy dx minus dy dx. Get all the dy dx terms together. Equals 1 minus 3x squared y to the third. And, how do we solve for dy dx? Well, we factor it out. Take it out of both of those terms, and here's what's left. And then we divide out everything that we don't want. So dy dx is left, and it's equal to 1 minus 3x squared y to the third over x squared 3y squared minus 1. There we go. There's the derivative of y with respect to x, and this is all the stuff that's on this side. So if I knew a point on the graph, xy, then I could take the x and put it here and here, the y put it there and there, and I would have the slope of the tangent line at that point. Alright, enough of number 7. Let's do another one. Number 13. Sin of x equals x times 1 plus the tangent of y. Okay, so again, if I wanted to state this implicitly, I'd have to divide both sides by x, subtract 1, take the inverse tangent, and it just would be an incredibly messy looking thing. It'd be way more complicated to take the derivative of that thing then it would just be take it implicitly, take the derivative of both sides. So we take the derivative of this, and then the derivative of this, right? It's not really, you can't really separate it because it's all together. I can take the derivatives individually if they were added together or subtracted, but they're not here. So the derivative of this side with respect to x, I see it's just a function of x, and I know the derivative of the sine of x is cosine x, and then we move on. We've got a function of x times a function of x, right? Because it's implied that y is a function of x, that if I knew what x was, there might be this complicated looking expression that would tell me what y is. It's implied that it's out there somewhere. But rather than having to figure that one out, we just say, oh, it's a function of x, and we'll use the chain rule on this. But first, we have to take the derivative of this big thing. It's a function times a function, so we're going to use the product rule. So derivative of x is just 1, okay, and then multiply that by 1 plus tangent y. And then add on to that the function here times the derivative of this. The derivative of 1 is 0 plus the derivative of the tangent of something is the secant squared of that something. Remember that from the last section, the chain rule. Times the derivative of the inside function, inside function being y. So we've got dy dx. And now we just need to solve for dy dx. So cosine of x minus 1 plus tangent of y. And this is just all multiplied together. So it's pretty simple to see. We could divide out everything that's not dy dx. X secant squared y equals dy dx. So if I knew some x, y point on the graph somewhere, I could find the slope at that point. 26 x cubed plus y cubed equals, 4xy plus 1. And they give us this point 2 comma 1, right? And I've said in these last two problems, if I had some x and y, I could find the slope of the tangent line. And that's what we're going to do at the end of this problem here. So taking the derivative of both sides with respect to x, this is plain Jane. There's an x here, so no tricky stuff, 3x squared. Plus, okay, now I've got a function of x in here. Now I've got this outside and inside function using the chain rule. Derivative of the outside, 3y squared, leaving the inside function alone. Multiply by the derivative of the inside function. So that side's done. And here we have 4x times y, so we've got a function times a function. So constant multiple rule says take 4, you can just multiply it by, once you find the derivative. So here we're going to find the derivative. Derivative of x is 1 times the function, second function, which is y, plus the first function times the derivative of the second function. And that's just dy dx. Derivative of y with respect to x is by definition dy dx. And plus the derivative of 1, which is 0. Now we need to isolate dy dx, which means we're going to have to distribute this 4. 3x squared plus 3y squared dy dx equals 4y plus 4x dy dx. Okay, and then I'm going to get the dy dx's together. I'm going to just put them over here. There's not really any rhyme or reason to it, just a preference. There's 4x dy dx. And of course, I've moved this by subtracting 3x squared. 4y. Let's see, wait, that's over there. So minus 3x squared. Factor out of dy dx. Equals 4y minus 3x squared over 3 squared minus 4x. Okay, whew, I did all of that. I took the derivative of both sides with respect to x. Remember to apply the chain rule when I see a y. And the derivative of y with respect to x is dy dx. Then I collect the dy dx's together, factored out a dy dx, and divide out what I don't want. And now the last part is, remember that they want the slope of the tangent line at this point. And that's just as simple as putting 2 and 1 in here in the appropriate places. So dy dx, I guess we could use like some weird notation just to remind us that at this point, and just please don't get confused by this. All I'm saying is dy dx, the slope of the tangent line, at the point 2, 1 is going to be what I'm about to plug in. 4 times 1 minus 3 times 2 squared over 3 times 1 squared minus 4 times 2. And we're running out of room, so we'll just do 4 minus 3 times 4 is 12, so 4 minus 12 is going to be 8. 4 minus 12 is going to be negative 8. And 3 minus 8 is going to be negative 5, so we have a positive 8/5 is our slope. Alright, moving on from 26, let's do 30. And I've got this cissoid, and its function is, its equation, and they give us this point, 2, 2, and here's a little recreation of the graph. It looks something like this, with a point right here, of course, at 2, 2. And it looks like a vertical asymptote at x equals 4. They want to know the slope of this tangent line at this point. So, let's help them out. We're going to take the derivative of this function. And we're starting to see, hey, here's a product. Going to use the product rule. Here's just a little function over here. So taking the product rule, the derivative of the first, which is just negative 1, times the second, plus the first, times the derivative of the second. So this is where we look at this and realize, yeah, this is a function of x, and it's squared, so I've got this outside function of squared applied to this inside function of y. This function called y, it's a function of x. Anyway, 2y, right, that's the derivative of something squared, 2 times the thing, times the derivative of that inside function, which is dy dx. And the derivative of this is 3x squared. And now we just need to solve for dy dx. So all this stuff is kind of attached to dy dx for the moment. We'll add y squared to both sides. 1 minus x times 2y times dy dx. And dy dx is equal to 3x squared plus y squared over this whole thing, 4 minus x times 2y. Is that it? Yeah, that's it. Just that. And the point 2, 2, we're going to find dy dx at 2, 2. And that is, we're going to plug in 2 for x's and y's. So we put a 2 in here, we get 3 times 4 plus 2 squared is also 4, and then 4 minus 2 would be 2 times 2 times y, 2 times 2, which would be 4. Alright, so we have 12 plus 4, that's going to be 16 over 2 times 4, that's 8, so we got a slope of 2, up 2 and over 1 at that point. let's go now. Okay, so I've highlighted 69 and 70 because it's good to talk about these things. We talked about 69 really already. It says describe the difference between an explicit form of a function and an implicit. So explicit, really simple. Y equals all this stuff, and this is, all x's over here, right? Only x's are involved over here. That is to say, if I knew x, I could put it through this machine here, run it through all these things, and find out what y is, right? It wouldn't make much sense to have y over here, because then I'd have to know y to find y, okay? So explicitly, we say y is this right here. No x, plug it into this thing that only has x's in it, and you can find y. An implicit one is just one that's not like that. Maybe there's a y over here, or maybe there's these y's that are pretty inseparable, and they're equal to x plus the tangent of y. Just y is all through the whole thing. It's not simply y equals. If it's not simply y equals a bunch of stuff with x in it, then it's implicit. There's some theoretical way to isolate y so that it's on one side and x's are on the other, but it would be so complicated, or sometimes, to what we know, impossible to do. Like, for instance, if y was to the fifth, there's nothing that we know of as far as the general quintic formula, like there is a quadratic formula. So it seems that's, at this point, at least in human history, it's impossible to do. So yeah. So when that happens, then we can't isolate y by itself. It's implicit. So when we have this implicit thing, number 70 asks, in your own words, state the guidelines for implicit differentiation. If you have some implicit function, y is just all over the place, and there's some x's, and some whatever, just all over the place, you find y. What do you do when it's not explicit like normal? Just take the derivative. Let's see. I would take the derivative of both sides with respect to x. Let's say remembering to apply the chain rule when you see y, right? When it's appropriate, you're taking the function, or taking the derivative of a function that involves y. Remember to use that chain rule. And to isolate dy dx. Or if you prefer to call it y prime, they're the same thing. I'd suggest thinking of it this way because it becomes useful when we start talking about differential equations in chapter 6, and so keep this in mind. So isolate dy dx like you'd isolate any other variable. Algebra stuff, it can be tricky sometimes, but definitely doable. So that's it. I hope that was helpful.